Hi, I'm Joel Galtieri.
I'm Wright.
I'm Seok Kim.
I'm Lingxue. I'm Zulidia Martinez.
I'm Richard Hochreiter, and this is the synthesis and characterization of biodiesel produced from waste cooking oil.
Biodiesel, a type of biofuel, is monoalkyl esters of long-chain fatty acids produced from various feedstocks and is intended as a substitute for common petroleum-based diesel. This alternative clean burning fuel is created from 100% renewable resource and is reducing U.S. dependence on foreign petroleum while also creating many new jobs. According to AmeriGreen Energy, it is the first and only EPA-designated advanced biofuel in commercial scale production across the country and the first to reach 1 billion gallons of annual production. Biodiesel can be used in its pure form and can also be mixed with conventional hydrocarbon-based diesel to create a blend. Both pure biodiesel and blends can be used in any practical diesel engines to serve purposes such as transportation, energy generation, and heating fuel. Blends with under 20% biodiesel can be used in diesel engines with little to no modification. Biodiesel can also be used to accelerate the rate of petroleum diesel degradation through co-metabolism. Biodiesel is one of the easiest alternative fuels to use, and there is a variety of feedstock sources that can be used to produce it. These feedstocks include virgin oil, waste vegetable or cooking oil, animal fats, algae, oil from halophytes, and more. The waste vegetable oil discarded from restaurants is becoming more popular as a feedstock for biodiesel, and many supporters propose that waste vegetable oil is the best raw material for its production, but currently the worldwide production of vegetable oil as a raw material for biodiesel fuel is not abundant enough to substitute for the liquid fossil fuel version of diesel. Biodiesel is steadily increasing in production and consumption all over the world, with the United States in the lead, producing an average of 940,000 barrels a day compared to Brazil, who's in second, producing around 450,000 barrels per day. Consumption has seen a rapid increase from 2010 to the present, with the United States consuming a little over 2 million gallons in 2016. The use of biodiesel is known for being environmentally friendly, which is true because of its decreased greenhouse gas emissions, overall lower pollution, and its faster biodegradation. This biofuel has been studied to have 45 to 65% lower greenhouse gas emissions than conventional petrol diesel, depending on the feedstock it was produced from. Biodiesel is also the only alternative to have effectively completed the health effects testing requirements of the Clean Air Act of 1990. Carbon dioxide gases are actually recycled through this process, and according to Berkeley Biodiesel, the plant feedstock used in the making of biofuel absorbs carbon dioxide from the atmosphere when it grows, and once the biomass is converted into biodiesel and burnt as fuel, the energy released is used to power an engine while the carbon dioxide is released back into the atmosphere. Biodegradation rates are also impressive, with around a 5 times faster rate than petroleum diesel studied over a span of 28 days, and through co-metabolism, biodiesel blends can assist and accelerate the rate of petrodiesel. The only negative impact on the environment due to biodiesel production is deforestation. This occurs if deforestation and monoculture farming techniques are used to grow biofuel crops. Examples of this include tropic forests being cleared to make room for oil palm plantations. This can in turn damage biodiversity and ecosystems by threatening many species of plants and animals.
Conversion of used vegetable oil to biodiesel is an important process for the production of biodiesel. Pyrolysis and transesterifications are possible methods for conversion. Pyrolysis is a method conducted at a high temperature with or without the aid of a catalyst that decomposes plant raw materials or animal fats into a series of mixtures. Alkenes, olefins, dienes, aromatics, and carboxylic acids are the possible products. This method must be carried out without air or oxygen to prevent the oil from being oxidized at high temperatures. The reaction conditions, such as rapid heating, break down the organic polymers in biomass into short-chain molecules, and these problems lead to the complex equipment and high production cost. Therefore, this method has not been appreciated by researchers due to its low conversion rate, high energy consumption, and poor economy. Another method that is widely used is called transesterification. Unused vegetable oil is first heated to remove impurities. Then they undergo a transesterification reaction in the presence of acid or base catalysts or other new catalysts. Finally, pure biodiesel fuel is obtained by washing and drying the corresponding fatty acid, methyl ester, or ethyl ester. The transesterification method can be divided into acid-base catalysts, enzymatic catalysts, and a supercritical methanol process based on the catalytic method. Although the esterification methods are different, their reaction mechanism is the same. The figure on the left shows the schematic diagram of transesterification mechanism. A triglyceride reacts with three molecules of alcohols in the presence of catalyst, producing a mixture of fatty acids, alkyl esters, and glycerol. The acid catalyzed transesterification process is a catalytic process by using strong acid to catalyze esterification of free fatty acids. This process has very slow reaction compared to that of base, and it is possible for the high free fatty acids but produces water. Unburned hydrocarbons and carbon monoxide are substantially reduced, and sulfur dioxide emissions are eliminated. The base catalyzed transesterification process is the most widely used technique. This process has faster reaction compared to that of acid, and this fast reaction leads to less corrosive. Recycling catalyst and possible formation of soap is challenging these days. The enzyme catalyzed transesterification uses enzymes to produce esters from triglycerides at relatively low temperature and pressure. It has relatively longer process compared to other reactions. The catalyst separation issues are solved easily, but the expensive catalyst is the disadvantage for this process. The supercritical methanol process is a non-catalytic process. This process is an economical, efficient, and environmentally friendly method for producing biodiesel fuel compared with the conventional commercial method. Moreover, no soaps generated, and separation and purification of the products are easy. Unlike the other methods, this method can also be applied to relatively long-chain alcohols due to the non-catalytic process.
Now I'm going to speak a little bit about the characteristics of biodiesel and how they compare to regular diesel. These characteristics include chemical composition and important fuel properties. For the chemical composition, HNMR spectroscopy tests for the presence of fatty acid methyl esters in biodiesel. FAMEs are what makes up biodiesel. IR spectroscopy is used to test for the presence of glycerol in the fuel. Gas chromatography coupled with mass spec determines the composition. For the fuel properties, the most important fuel property to consider is viscosity. Other properties included are cetane number, heat of combustion, and the cold flow properties such as cloud point and pour point. These graphs here are HNMR spectra of vegetable oil before and after the transesterification reaction. This data was actually collected by me during a project in a chemistry lab. Both the processed and unprocessed oil have almost the same hydrogen setup, which makes it difficult to distinguish between the two. The only real difference between the two is the singlet hydrogen on the FAME, which exists only for fatty acid methyl esters and not triglycerides. This is the characteristic peak that proves the trans-esterification reaction was successful and biodiesel was formed. In order to purify the product, the biodiesel mixture is centrifuged to remove the solid glycerol byproduct. The graph on the right is an IR spec of purified biodiesel. It's not very useful in determining if fatty acid methyl esters are created due to the similar structural nature of triglycerides and FAMEs. The graph on the left is an IR spec of the solids produced from the trans-esterification reaction. The graph very clearly shows the characteristic peak of the glycerol byproduct formed when fatty acid methyl esters are created. The data was also collected by me during a project in the chemistry lab. Gas chromatography coupled with mass spec is used to determine the composition of the produced biodiesel. The main component of biodiesel is fatty acid methyl esters. The composition of these FAMEs is completely dependent on the composition of the feedstock. Although it varies, the GCMS data on the right is a sample representation of the makeup of biodiesel. The main constituents are palmitic acid methyl ester, linoleic acid methyl ester, and stearic acid methyl ester. As I mentioned before, viscosity is the most important property of biodiesel. It affects the operation of fuel injection equipment, particularly at low temperatures when the increase in viscosity affects the fluidity of the fuel. The typical viscosity of biodiesel is 1.3 to 1.6 times higher than that of traditional diesel. Lowering the viscosity of biodiesel without changing any of its fuel properties is currently a growing area of research. Cetane number is a measure of ignition quality or ignition delay and is related to the time required for a liquid fuel to ignite after injection into a compression ignition engine. High cetane number implies short ignition delay. The cetane number of biodiesel depends on the distribution of fatty acids in the original oil or fat from which it was produced. The longer the fatty acid carbon chains and the more saturated the molecules, the higher the cetane number. The broad range of cetane numbers for biodiesel commonly cause issues with the timing of engines. The heat of combustion of a fuel measures the energy content. Higher is generally better. The table here shows the heat of combustion for biodiesel, regular diesel, and gasoline. The heat of combustion for biodiesel is slightly less than regular diesel. This is because biodiesel is an oxygenated fuel. This means it's a fuel with less energy but burns more completely. Some of the cold temperature characteristics of biodiesel are cloud point and pour point. Cloud point is the temperature at which a cloud of crystals first appears in a liquid when cooled. Pour point is the temperature at which the amount of wax out of solution is sufficient to gel the fuel. Thus, it is the lowest temperature at which the fuel can flow. Both cloud point and pour point are considerably higher than regular diesel. This is also a large area of research into biodiesel. For this reason, a fuel that is 100% biodiesel cannot be used in a combustion engine in colder time climates.
Although there are many advantages both to consumers and the environment to using biodiesel, there are some disadvantages as well. One of the main advantages of biodiesel is that on average it is cleaner than fossil fuels. However, biodiesel does have about 10% more nitrogen oxide emissions than fossil fuels. This could cause increase of both smog and acid rain in largely populated areas. One big problem is that the oils in the biodiesel will turn to gel at around 40 degrees Fahrenheit, whereas diesel has a gelation point of around 4 to 13 degrees Fahrenheit. There are slight differences of the gelation point due to the varying compositions of biodiesel. The various compositions of biodiesel also pose more complications. For example, restaurant fryer oil contains more fatty acids that will increase the chances of saponification, or the creation of soap. Residential cooking oil, on the other hand, contains more water. An increase in water impedes the biodiesel reaction, which can lead to only a partial conversion of the oil into biodiesel. Water in biodiesel can also cause a decrease in the heat of combustion, an increase in bacterial growth, and deterioration of fuel system components. Biodiesel can only be used in diesel-powered vehicles, and there are still a lot of complications when it comes to using biodiesel in a car. Besides the gelation point, limiting the use of biodiesel to warm temperatures, there are also precautions that need to be taken in terms of the equipment in the car engine. Currently, cars are only allowed to use a maximum of B20 or a biodiesel diesel mix that contains only 20% biodiesel. Degradation of rubber hoses and gaskets is another huge concern when it comes to using biodiesel in car engines. Biodiesel has been proven to be incompatible with both butadiene and nitrile rubber. Biodiesel also cleans dirt from the engine, which means that the filter must be changed after the first few hours of using biodiesel, as to avoid a buildup of dirt and the clogging of a filter. The ignition timing of a vehicle must also be adjusted, since biofuel mixtures and straight diesel have different compositions and therefore ignition temperatures. Biodiesel has also been known to lead to slightly lower miles per gallon than standard diesel due to the low energy content. Animal-based biodiesel averages about 10.6 less miles per gallon than petrodiesel. There are several ways to combat these disadvantages. Fuel additives can be used in order to reduce the deposit levels. Cold flow additives can also be used in order to lower the gelation point, but these additives must be matched based on the composition of the fuel, which can mean more time, energy, and money. Another possible solution is filtering or skimming off the gelatinous part of the biodiesel in order to separate it into various batches according to the temperatures at which they can be used without turning into gel. The last possible solution, as I mentioned previously, is biodiesel mixing. This can be used in order to lower the gelation point and decrease the problem with car engines.
The cost of feedstocks is a major restricting factor in the development of biodiesel because the most common commercial process of biodiesel production is homogeneous alkali catalyzed transesterification, using refined vegetable oils as raw materials. Each finished gallon of biodiesel produced will require slightly over 1 gallon of feedstock, either new vegetable oil or filtered waste fryer oil from restaurants. Prospective biodiesel producers should consider the amount of fuel they hope to produce, and then be certain that they will be able to obtain and handle the necessary feedstock oil on a regular basis. As production volumes increase, the logistics of collecting large amounts of waste fryer oil might become more cumbersome. In addition, as more people produce biodiesel, there might be competition for waste fryer oils. Lastly, it should be noted that working with used cooking oil is somewhat more complicated than virgin oils due to the varying acidity, moisture content, and quality of used oil. Inflation is defined as the increase in a currency supply relative to the number of people using it. As a result of this supply inflation, the general price level of goods and services in an economy over a period of time will rise. Then the prices level rises. Each unit of currency buys fewer goods and services. Inflation rate for operation, material prices, catalysis, chemicals, and feedstock is considered to be 3% of its price, while labor inflation rate will be 8% as seen in table number 1. The assumptions made for our product will be executed by 49% equity, 51% debt, with loan interest 9%, which is high value as in most products the loan interest is 6%, and the debt repayment period of or payback will be 8 years. So our product is designed to process 101,000 tons of used cooking oil and 26,800 tons of methanol to produce 1,000 tons of biodiesel. Those were our assumptions. The amount of cooling water and processed water used during our production will be at most 1 million cubic meters per year, and steam for heat exchanging will be around 300,000 tons per year. Our chemical cost will be at most 3 million per year and area of land 42,000 square meters that equal 10 feet in, as shown in table number 2. For table number 3, what we did was just making assumptions for the number of laborers, like 150, and an average salary per year, per month, and per year. Our Our project presents a detailed cost analysis for a biodiesel plant with a capacity of 100,000 tons per year, as I mentioned before. The cost analysis basis depends on the optimum conditions obtained from the experimental work that achieves biodiesel conversion to approximately like 99%. This concludes that our project will achieve a good income that around $4 million per year, and the total net income during the life cycle of the project would be $72,500. And making an assumption of an estimation of production per 1 liter biodiesel would be 7.2 cents per liter, and for waste cooking oil cost will be $0.33 per year. Also, our production of 1 liter biodiesel from cooking oil is $0.5, while the global price of biodiesel is like 0.68, and global biodiesel current price like $1 per liter. Operating costs, as it can be seen, are the expenses related to the operation of the plant. It's divided into the fixed and variable costs, and as described in the table, it can be seen that the fixed costs are those incurred whether the plant is in production or not, and are at a constant level, regardless of the output produced, such as salaries or rents being paid per month. And the variable costs vary at a rate directly related to the production of the plant. They are incurred only when the plant is in operation, although some costs, such as interest, maintenance, and repair, have fixed costs, while maintenance and repair are considerable variable costs. As it can be seen in the graph, the vegetable oil is increasing over the years. For like in 2018, like 29 approximately billion liters, and for 2018, it would be like 30 to 31 billion liters per year. As we know by now, the waste byproduct of making biodiesel is raw glycerol. This is the raw form of glycerin, which is used in many chemical applications from explosives to soap. Many people ask what to do with the raw waste byproduct, as commercially glycerin is distilled and purified by a high temperature, high pressure steam distillation process, which is well beyond the scope for most home biodiesel brewers. Now, we will see some uses of the raw glycerol product that have been used by others. First, we need to know that glycerol is a major byproduct in the biodiesel manufacturing process, and each gallon of biodiesel produced approximately has 1/5 gallon of glycerol. And refining crude biodiesel glycerol into pure is not considered practical on small scales. So one of the uses might be that it can be useful for making soaps and animal feedstuff, and using glycerol as a feed ingredient for animal dates back into the 1970s. However, glycerol's utilization in feed has been limited by availability of itself. Recently, the possibilities of using crude glycerol from biodiesel in feeds have been investigated because of the increase in the price of corn and the surplus of crude oil, crude glycerol. Also, it is used as a lawn fertilizer and weed and grass killer when it's mixed with sodium hydroxide and potassium hydroxide. Accelerating change into utilization of biodiesel from waste cooking oil will have a great profit and positive effect on environment, vehicle engines, independency on crude oil, investment in economy, as it will increase jobs and save foreign currency, especially that the assumption of biodiesel is very high, as we said before. For example, we can say that the consumption of biodiesel is like 13.5 million tons in 2014. It's imported 25 of diesel and 75% from local markets.
Vegetable oil is used directly at the field in other modified or unmodified equipment. It is referred as the straight vegetable oil (SVO) or pure plant oil (PPO). Many cars powered by a direct injection engine supplied by inline injection pumps are capable of running on pure SVO or PPO in all but winter temperatures. Principally, the viscosity and the surface tension of the SVO or PPO must be reduced by preheating it, typically by using waste heat from the engine or electricity. Otherwise, poor incomplete combustion and carbonization may result. Co-solvent bleeding is a low-cost and easy-to-adapt technology that reduces viscosity by diluting the vegetable oil with a low molecular weight solvent. Many restaurants will receive a minimal amount for their used cooking oil, and processing to biodiesel is fairly simple and inexpensive. Recycled vegetable oil, also termed used vegetable oil (UVO), vast vegetable oil (WVO), used cooking oil (UCO). As of 2000, the United States was producing in excess of 11 billion liters (2.9 billion US gallons) of recycled vegetable oil annually, mainly from industrial deep fryer in potato processing plants, snack food factories, and fast food restaurants. Virgin vegetable oil, also termed pure plant oil or straight vegetable oil, is extracted from plants solely for use as fuel. In contrast to used vegetable oil, it is not a byproduct of other industrial, and thus its prospects for use as fuel are not limited by the capacities of other industrials. Production of vegetable oils for use as fuels is limited only by the agricultural capacity of the given economy. However, doing so detracts from the supply of other uses of pure vegetable oil. Vegetable oils are increasingly used as a substitute for fossil fuels. Vegetable oils are the basics of biodiesel, which can be used like conventional diesel. Electricity generation it's only used in peaking power plants and small power plants. Other methods like nuclear power, fusion power, wind power, and solar power may provide cheaper electricity. Germany used to have 0% taxation, resulting in it being a leader in most developments of the fuel use. And it is illegal to produce any fuel if it is not to be sold unless a license to do so is granted by the federal government in Australia. There is a concern that the current growing demand for vegetable oil is causing deforestation, with old forests being replaced with oil palms. When land is cleared, it is often burned, which releases large amounts of the greenhouse gas, carbon dioxide. The food versus fuel is a dilemma regarding the risk of the diverting farmland or crops for biofuels production to the detriment of the food supply. Several studies do show that the biofuel production can be significantly increased without the increased acreage, therefore stating that the crisis in hand relies on the food scarcity.